Hi class, welcome back. We're now going to do part B of angular and linear speed. We already have found the angular speed given the radius and the linear speed. So now what we're going to do is change that angular speed that is given in 1408 radians per minute. We want to now rewrite that so we can do it in revolutions per minute. So I'm going to open up math type so we can see what conversion card we would need to use in order to go from radians per minute to revolutions per minute. So it turns out we know that one revolution is equal to 2 pi radians. And so we're going to multiply the 1408 radians per minute by the appropriate conversion card so that we can have the right units cancel. I want to cancel the minutes. Pardon me, that's not true. I want to cancel the radians because I want revolutions per minute. So the minutes we want to keep, it's the radians we want to get rid of. So since radians are in the numerator, I am going to make sure I have radians in the denominator. And therefore that means the 2 pi will be in the denominator. So 2 pi radians. And so then I can cancel the radians. And when I cancel the radians, that's going to leave me with 1408 over 2 pi revolutions per minute. And so what we'll do is we'll go ahead and divide 1408 divided by 2 pi, and that'll change the radians per minute into revolutions per minute. So if we already have the radians per minute, all we need to do is divide by 2 pi. And then we have 224.09. And then they says don't round any intermediate computation, so don't change the pi to 3.14 and then do the computation. They say just round to the nearest whole number, which would be 224. All right, let's do another. In this example, we have a Ferris wheel at a carnival, and it's 29 feet long, and it is traveling at 69 miles per hour. Again, this one's kind of very similar, that they're giving us the radius in a certain number of units, and then they're giving us miles per hour, which is linear speed. So let's do one where that's not linear speed. So let's hit explain, and then do one more practice. All right, so this is good. This one they give us the rotates on this axis once every 6 days. The equator lies at a radius. So in this one, we're not having linear speed. We are having this rotation, and rotation of once every 6 days lets us know that's going to be something different. That's angular speed. So let's open up math type to capture that. So rotates one revolution or once every 6 days. So that's one revolution every 6 days. So one revolution every 6 days. That's one piece of information that we're given in the problem. But we're also given that the equator lies on the circle with a radius of 700 miles. So the radius is 700 miles. And then the first thing that we're asked to find is the angular speed in radians per year. So we want to know the angular speed in radians per year. I have per year. Well, there's a relationship between days, which I have in the numerator, and years. And it turns out there are 365 days in 1 year. So we'll capture that. So now my units will cancel. The days will cancel. The revolutions will cancel. And so I have 2 pi times 365 over 6, and it's going to be in radians per year. So let's go out to the Alex calculator and do that computation. 2 pi times 365 divided by 6. So about 382 radians per year, Or if we round that to the nearest whole number, because I believe they ask us to do that in this example, so it would be 382. The next example says, now let's find the linear speed in miles per year. So there's a relationship between linear speed and angular speed, and that's the formula that V equals R times omega. So that's my futile attempt to draw an omega. All right, and so we know that R is 700 miles. And we know our omega is equal to, and that one there has intermediate computations. That's a computation. So I'd like to go back and put in the value without that intermediate computation. So I'm going to hit undo on the calculator. Pull out my eraser to get rid of this. And so that represents radians per year. And we want miles per year. So I'm going to multiply that 700 times 2 pi times 365. So 2 pi times 365, and I'll just put it in parentheses, divided by 6. So it's going to be 700 times 2 pi divided by, times 365 divided by 6. And that will give me miles per year. And you said, well, how do you know it's miles? Because the 700 was in miles. So let's write that unit there. And so when we do that computation, we get 267, 558.97. If we round to the nearest whole number, it would be 267, 559. So it is booking. It is moving at 267,559 miles per year. All right, one more. So in this one, we have an 18-inch blade. The radius is 18 inches. I think we did this one in class, so let's hit explain and do another. All right, yes. So we have a cyclist is riding a bicycle whose wheel has a diameter of 24 inches. So the wheel has a diameter of 24 inches, so we're going to grab that piece of information. It's also traveling at 29 miles per hour. So it's traveling at 29 miles per hour. So remember that it's per hours. And they want us to find the angular speed. So we have the 29 miles per hour, which means that we're given V. So V is equal to R omega. And I'll just write it as a W, but it really is the Greek letter omega. And but we also know that V is equal to 29 miles per hour. So I'm going to rewrite the 29 miles per hour is equal to the radius. In this particular case, we know that the diameter is 24. So if the diameter is 24, then that lets me know that the radius will be half of that. So the radius will be 12 inches. I'm going to put in the 12 inches times omega, which I'll represent using W. So now what I'm going to do is I want the angular speed, which is omega, and then I'm going to solve for that by dividing both sides of the equation by 12. So I'll divide both sides by 12 inches. On the right-hand side, it's going to cancel. And on the left-hand side, I have 29 miles per hour. I guess I left off the miles per hour, sorry. Miles per hour divided by 12 inches. So let me go out to math type to capture it so it looks more authentic. Now that I have math type opened up, I have V equals R omega. I have 29 miles per hour is equal to 12 inches times omega, and I divided both sides by 12. When I divide both sides by 12 inches, they cancel on the right. And then I have 29 over 12 inches in miles per hour. So now I have omega in miles per inch hours. And so what I want to do is I want to cancel out the units, but I need to see, well, what units do they want me to give the angular speed omega in? So when I look back to Alex, it says that they want it in radians per minute. So if they want it in radians per minute, I need to convert that hour that I have. So I want it in minutes. Yeah, radians per minute. So I know of hours and minutes. Well, there's a conversion or relationship between hours and minutes. We know that 1 hour, and notice that I'm writing the hour in the numerator, so it'll cancel with the hour in the denominator, is 60 minutes. So now I'm going to have the hours taken care of, but now I've got this miles inches. Well, I know that miles has a relationship with feet, and I also know that inches has a relationship with feet. So I'm going to multiply by to convert that inches into feet. So that I know that 12 inches is equal to 1 foot. And then I also know that 5,280 feet are in a mile, and they also give it to us in the problem. I'm going to write that 5280 in the numerator so that the feet in the numerator will cancel. And I wanted the miles to begin with because I wanted a relationship that can convert miles to feet. So now I can pull out my rusty dusty counselor machine. So I can cancel the inches, the feet, the miles, and the hours. So then all I have left is number on top, no units, per minute. And remember that radian really doesn't have a unit of measure. So if there's no units in the numerator, it can be thought of as the number in the numerator would represent the radians. So I have 29 times 12 times 5280 all over 12 times 60. Just to make it so that I don't have to remember so much that I need to cancel, I'm going to cancel one more creature. I'll change it pink. I have a 12 feet here and a 12 feet here, so I'm going to cancel the 12 feet. All right, and if I really wanted to, I could cancel the 0, but I'll leave it. So I'm going to just do 29 times 5280 over 60. So that's 29 times 5280 over 60 times 5280. That's almost going to be about half because 30 over 60 would be 1/2. So it's almost going to be half of 5280. All right, so we get 2252 radians per minute. Now we want to know the number of revolutions the wheels makes per minute. So we already have radians per minute, and there's a relationship between radians and revolution. So we know that 1 revolution is 2 pi radians. So we're going to use that conversion card to convert the 2552 radians per minute. If I have the radians in the numerator, then I need radians in the denominator, and 2 pi is tied to the radians. So it's going to be 2 pi, and then that's going to be 1 revolution. So the radians will cancel, that 2 pi is in radians, and so we can cancel the radians. And now I have revolutions per minute. So once you have radians per minute, you just divide by 2 pi. If you had revolutions per minute, you would multiply by 2 pi. So our answer is going to be 2552 divided by 2 pi. So it's approximately 406.163, and we round to the nearest a whole number, it's 406. So I hope this movie on linear and angular speed is helpful.